did not use sort to solve this problem. I tried to use the table. However, the answer was wrong. So
yeah, the table would be too inaccurate, I think, for you to get any kind of number that would work. So what you've got here is n is 26. Oh, something's gone somewhere. N is 26 and the t is 2.10 and you're doing a greater than. Okay. So you're doing a greater than essentially 2.10. Okay, hit the solve button.
Okay.
Go to once, not inferential actually, although you would think that. Go to the distribution calculator. Go to t distribution. Right. The degrees of freedom are going to be 25 because there's 26 numbers in your sample, and degrees of freedom are one less than that. So you type in 25. You want to be greater than 2.10. So you should be able to go to the right hand side and choose right-tailed. No, not there. No, go move your mouse pointer to the right hand side and hit the dot that says right-tailed. Now go to the probability one and type in the 2.1 that you had there. Think of that X as saying T, and it's saying what's the probability that you get bigger than 2.1. Now that decimal 0.0229, that is the guy that you're looking for. That's your p-value.
So why this one we need to use t distribution, not use the integral?
You didn't use the other one because in this story, they never gave you the kind of information that you would need to be able to do the inferential. You don't know what number the mean is for starters. So you need to make that 230, I think, if you round off. So the 9 gets rounded up, so it becomes 30. Okay, do a check on that, just make sure I am correct.
Oh, I have only one shot. I did not. I need to fix the other one too. The other one was like.
No, that's okay. I can fix that for you later. So just scroll down to the part where you do a check.
So this one was like negative. So should it be?
Well, if that's if it's a well, you're jumping around a little bit, so I'm not quite sure where you are now.
Right. So when you use the solve to fix a problem, so at what point use integral or the other one? It's just according to read the question part?
The only time you would actually use that method that we just talked about here, there you go, is when you are not given the right information, when all you're essentially given is the sample size and the t-score, as you are here. And it's greater than or less than as well. When you're told that and you've been asked to find the p-value, you would use this setup here. If you were told the mean, the standard deviation, all that good stuff, things like that, the usual typical question, actually, the vast majority are the inferential ones, then you would use that. So that would be essentially when you would use one compared to the other.
Okay, thank you.
Now, I'm going to get started right now. So I'm going to take back control. Here we go. And let's look at what we're going to deal with today, which is 13A. So we're going to look at first hypothesis testing for a single mean, and then I'll get started on the next one, which is hypothesis testing for the difference between two means. But let's look at this one here. Right, a typical story might look something like this. That in the past, you know that the population mean was, say, 100. So let's talk about, it was the IQ story, which I kind of like. So that was in the past. The IQ used to be 100. And now we believe that it has got bigger in this case. So we're going to test to see whether there is enough evidence to show that the IQs, the mean IQ now has got larger, got more. So you would set up your null hypothesis as it's still 100. And your alternate one would be the one that you believe the changes. In this case, it's a greater than 100. And you collect a sample. And let's say you collect 250 people. And that the mean of your sample was 105. And that the standard deviation was 5. So you would be given this information in the story. You should also be given what significance level you're going to test for. And it's called alpha, the significance level. In this case, let's say you were told that you were going to do it with a significance level of 1%. Okay, I'm trying to get Olivia in here if I can. There she goes. So that is basic what a typical hypothesis test looks like. You're told something used to be true, you think it's changed in some way. This is what your null alternate is going to look like. This is the information that you've collected to try and see if you can prove that there has been an increase. So what we now are going to do is show you how salt could be used to do the analysis. And we're going to use the inferential statistics once I figure out which window I'm meant to be clicking on. Right, here we go. So this one happens to be question 9, but don't worry about what question it is. That's me just entering the homework. For the story that I've just given you, you tick the salt button. And you would choose, as you typically do for almost all these questions, you would choose, go away, ad blocker. You would choose one, oh dear. You would choose inferential statistics, there we go. And then you would pick one sample T. Whenever you are doing mean stories, right? Stories to do with a single mean, it's a one sample T. Now in this story, the sample mean was 105. The standard deviation in this story was 5. And in the sample size, it was 250. These are the numbers that I had in my box. These you're given. It's going to be a hypothesis test, right? And the mean in this story is 100. That's the status quo. You always put the null hypothesis there. And the alternate we're trying to do is, has it got bigger? So that's how you would put the hypothesis test that we described in my story about the IQs. That's the sample mean, that's the sample standard deviation, that's the sample size. This is what it used to be. Can we prove it's greater? So when I hit generate results, here is all the good stuff. One of the interesting things, the most interesting thing, is that number there. And what we would look at almost always is the value of the p-value. And it's 0.00001. It's darn close to being nothing, which is perfect. So if I now return back to the whiteboard, yeah. Now I know the p-value. We finish by doing our test. And the test is the same for every hypothesis test that you're ever going to make. is the p-value for the story, is it less than this significance level? And in this case, it is less than 1%. So when you say yes, you can finish with, there is enough evidence to reject H0. Now, what that sentence means, there is enough evidence to reject H0, it means that this, the alternate, is true. In other words, we've actually proved that the IQ has increased. You go and publish a paper and tell people what you've discovered, and you're all happy because you've got some useful result. And that's pretty much the one I've got here. That's pretty much the standard look. That's what you would be expecting to see in a typical hypothesis test from start to finish. Any questions about that before we go to the homework and maybe do some more at least? Are we comfortable about the strategy, how that becomes solved, especially if these numbers get used in solve? Okay, then I am going to move on and we are going to look at some homework questions. No particular. Is this a double I'm in? That looks interesting. Let me just check I'm in the right place. I am 13A. Okay, it's not a double. Okay. Let's look at question 11. It has been hypothesized that the mean pulse rate for college students is about 71. A sample of university students recorded, including their gender, and assume that the sample is representative of university students. We're going to find the test statistic for just males. So forget that top row, it's nothing to do with this story. We're just going to focus on males, right? And we're going to get the test statistic and its p-value, and then we'll finish off with this sentence, right? So what do we have? What do we know for males? Well, their sample size was 56. That the average for them is 70.32, and that the standard deviation was 9.75. And we are trying to test here whether or not the pulse rate for all male students have a mean of 71. And what we're trying to do, we're trying to check, I'm trying to see whether we're trying to prove is it more or less than 71 or just different. There's the keyword, whether or not the pulse rates. So that means they're just different, right? They could have said that they're less, which is what I would guess they would do in this story. So I'm hitting the salt. It's already on inferential statistics. It's already on one sample. So I would put in this case, 70.32. The standard deviation is 9.75. And the sample size is 56. And we want to see whether or not it's different from the 71 that they mentioned. My gut feeling is that this is not going to be significant. Why do you think my gut feeling is that the p-value is not going to be that small? Why do you think I can make that assumption? We're going to find out if I'm right in a minute. What made me decide to say that? No ideas? Okay. Isn't 70.32 really close to 71? And isn't that really quite a small sample size? And just to add insult to injury, isn't that quite a large standard deviation when you compare the size of the data? Now, all those things are probably going to mean that we are not going to get a decent p-value. Decent in the world of hypothesis testing is you want it to be tiny. That's good evidence. And the p-value that I got was 0.6. Would you agree that that is not good? So the two numbers that we would be using are the test statistic, would copy this guy, and the p-value, which is this one. So here it goes. The test statistic is a negative number, which it can be. And I'll put that in and round it off to 2 decimal places. And then the p-value, I'll put that in and I'll round that off to 4 decimal places, so 6038. Now, compare it against a 5%. Well, is 0.60 less than that? Nope. And when it's not, you fail to reject, and there's insufficient evidence. Are we comfortable with what we did there? Does that make sense? Okay, do you think the women have maybe a better chance? Let's find out. Find it testing or not, whether or not. So in this case, we're going to look at the women now. The sample size is even smaller, which isn't good news. But isn't that quite a big difference from 71? Right? And the standard deviation is high. So, you know, it's a 50-50. So I'm just writing down the numbers I'm going to use. A mean of 34. Sample size is 34. A mean is 76.8 and a standard deviation 11.5. So here's we go. We'll hit salt. I'll put in the mean 76.8. Put in the standard deviation, which is 11.5, and a sample size of 34. And we're doing the same check. Is it different from 71, right? So when I do the generate results, a little bit better. Would you agree that's a much better p-value? And in our world, better just means it's nice and small. So the test statistic, which you can't see anymore, but I'm copying and pasting, goes here. And that's 2.94 to 2 decimal places. And the p-value, which I'm copying now, was nice and small. And to 4 decimal places, it becomes that. Now we're comparing this decimal to that guy. Now, is 0.0059 less than that? And the answer is yes, it is. And that means that you will reject the null hypothesis, reject H naught. And that means we can say or conclude that the mean pulse rate is not 71, right? It's different from 71. Now you might say, what's wrong with maybe that one? Because it looks the same. And the missing word, or the wrong word, is insufficient evidence. When you reject H naught, you're doing it only because there was sufficient evidence.
You're not sharing your screen with us.
Ah, darn it in space. What am I sharing? Because I don't know what I'm sharing right now.
We can just see you. That's about it.
Okay. Can you see it now?
Yes, we can.
Did you see all that button pressing that I did before that to get these two numbers?
We did not.
You did not. Okay. So here is what I typed in. One sample T, there's the sample mean for the women, there's the standard deviation and the sample size, and we're checking hypothesis test that it's different from 71. When you hit generate, that's the T statistic and that's the P value. So if I now move this out the way, are you comfortable where these guys came from? Okay. It says, is the hypothesis test in this situation one in which a decision leading to an action is required? I'm not quite sure what they mean by that, to be honest. My gut feeling is that the fact that we couldn't prove it for the males, but we could prove that it was different for the females. I'm not sure what action you could do about that, except saying, well, I guess that's interesting. So I'd go for one of those that says no and see which one it is. Okay, let's do another one of these guys. This is question 12. I'll see if I can make it a little bit bigger to easier to everyone, including me, to read. Here we go. This story says that many cars have a recommended tire pressure of 32 pounds per square inch, PSIs. Okay? You got a car, you probably knew that. 32. If you didn't, and you go to a garage and you want to check your tire pressure, 32 is a good number, right? What they're interested in here is a vehicle safety checkpoint. Officials plan to randomly select 55 cars, and they're going to measure them, and they want to know whether drivers on average have too little pressure in their tires. So we're looking for proving, see if there's evidence at least, that it's less than the standard value, which is 32. And in this story, the 55 cars came out with a 29.3 and a standard deviation of 3. So all the information that we need for SALT is here. Sample size, sample mean, sample standard deviation. And later on, we're going to use that guy as our test. Okay, so let's set this thing up. We are going to type in the null hypothesis, which is mu equals 32. So now I have to find out the Greek letters and find mu. So if you're wondering where mu is, it's in Greek letters. And it's equal to 32. And we are going to check, is mu less than 32, right? That was, oops, too many less than's. We're going to check that guy as our alternate, right? Because, you know, we think that actually people underinflate their tires. Are we okay with that? The null is what it should be, and we think there's evidence to prove that it's less than that. So I'm now going to hit use SALT button. I'm going to bring it here so you can see it. And I'm going to type in the sample, and the 55 guys that they checked, the cars, are 29.3. And the standard deviation was 3. And they did it for 55 cars. And the 32, and we're trying to show that it's less than. Are you happy about where those numbers came from the story we just talked about? Okay. Now, when I hit generate results, whoa, look at that T statistic and look at how small that P value is. You agree that's going to be good news for this one? Right. So I'll move that out of the way and I'll put that information in. So our test statistic going to be that number to 2 decimal places. And our p-value to 4 decimal places ends up being 0.0000. I know that's 0, but we're rounding it off to 4 decimal places, and I'm indicating that by those 4 zeros I've got. Now, on the basis of this p-value, is 0 less than that guy? Yes, it is, isn't it? 0 is less than significance level. So you reject the null hypothesis, yep, because the p-value is smaller than 0.05. So that's the right one to choose. And we can conclude that the average driver with this type of tire have too little pressure in their car, their tires. So they were right. So maybe if that was an actionable one like the previous question, I could see this resulting in an action. Can you imagine they would first tell the driver, do you know your tires are a bit in the flat side? But more than that, wouldn't that maybe be, maybe we should do an advertising campaign directed at motorists, something along the lines of, you know, tire pressure is important, you know, you make sure your tires are the right pressure, go get them checked, you know, things like that. One of those kind of things to try and encourage people to not have these low numbers. That one 14 is really a duplicate of that one. Let's try this one then. Make this the last one of the single mean hypothesis test, and then we're on to our last topic. The last one in the set. Okay, a lot of reading in this, so while I'm reading it, I'll get my piece of paper and start writing down the key numbers. A cell company knows that the mean length of call for its customers is 9.4 minutes. So you've just told me that the population mean used to be or is 9.4. They're thinking about doing a discount for older folk. And using this method, the company contacted a random sample of 100 people, right? There's that, 100 people. And they recorded the lengths, and the average was 8.2. And the standard deviation was 10. So pretty much that piece of the sentence has all the numbers that we need. Great. It's got the sample size, the mean, the standard deviation. It looks like oh, I just noticed something. This piece of information is slightly different than the one that's up here. You notice that? And this mentions 100 calls. And this mentions that they contacted 400 seniors. Interesting. Wonder where this is going to go. Let's do the first one. Carry out a test of the hypothesis of interest in the situation where 400 seniors were surveyed. So if it's going to be 400 seniors, you're going to do the mu. Where is mu? Where mu is equal to 9.4. And mu is less than, I believe. And the reason I'm going that direction is, aren't seniors spend on average less time than 9.4 minutes on a call? And if I use the information that they've got, which is basically this up here, I have a decision to make. Is the sample size 400 or is it 100? Which of those two is it? It's not a trick question.
400.
Yeah.
Say what situation.
Yeah, can you see that one? Okay, so I'm going to hit salt now. I'm going to bring this guy over. I think I've got all the numbers that I need. It's going to have a mean of 8.2. Standard deviation happens to be 10. 10? That seems a bit on the big side, does it? Yeah, that is really a huge amount. And 400. And we are going to be putting in here what it used to be. And are we going to do not equal to or less than? We said less than, so that's the one I'm going for. And I'm going to go generate results. Here's your test statistic, and here's your p-value. So put in test statistic, which is about 2.9. 4 decimal places. Here's your p-value. Four decimal places, right? Is this guy less than 0.05? Yes, it is. And so we're going to reject it, and we're done. Basically, we've shown that older people typically spend less than the average 9.4 on the phone. And if you did it with the original 100, the p-value ended up being that number. So you're not even going to use salt. They're just telling you what you would have got if you had done salt. Do you notice that that number is too big? So what's the moral of that story is, if you do a sample of 100, you might not get enough evidence. But if you increase your sample size to 400, you could end up with evidence if it's there. Of course, if it's not true, right, if whatever you think is true, if it's not true, couldn't you pick the biggest sample in the universe and it still won't get you evidence, right? If you go the wrong direction, you really shouldn't be able to find evidence to prove something's right when it's not. But it can happen if it's very close to the number. If you think it's a little bit bigger or a little bit less, you might get that just by the sheer randomness of samples. Are we good with that questions? Are we happy with the process for single means? Then that means if we are, what we are, that there's only one last guy to do. And let's get it set up. We're going to look at hypothesis testing for the difference between two means. Well, let's do a little bit of theory before we get too caught up on the details, because there's a lot of stuff. Try and move this a little bit. Too much. Just tweaking this. Okay, that'll have to do. Right, well, what's the difference? It's very similar to the two proportion ones. You're going to have two populations. Call it population 1. We'll call this guy population 2. And we're interested in testing, is there any significant difference between the two populations parameter? And the parameter that we're going to deal with is the mean. So it could be the mean ages of the two populations, the mean height, the mean weight, the mean number of cars they've got, whatever it might be, it'll be a mean. So you're going to have mu1, which is the population mean for this one, and you're going to have another guy called mu2. And that's the terminology that we would use. And so how do we decide, for instance, what kind of differences there might be? Well, there are 3 versions of the hypothesis test. And each one depends on what evidence you think you're being given. So you've been given evidence that they're just different, that one is bigger than the other or one is smaller than the other. So all of these begin with a null hypothesis that looks like that. You assume that there is no difference between the two population means. Now, I could have called that mu1 equals mu2, but we tend to write that down as mu1 take away mu2 is 0. And the alternate is written down in the same vein, but greater than 0, in which case it's called a right-tailed test. The second version of hypothesis test is that it's less than 0. And I've just called, I've just called it correct. I'll take my mind back. It's called a left-tailed test. I think they just call them one-tailed in this one. And the last possibility is that, they're equal or they're not the same. And that's called a two-tailed. If you look back at your notes on the hypothesis test for the difference between two proportions, doesn't that look remarkably similar? Would you agree it looks very like what you would do, but P1 take away P2. Here it's going to be mu1 take away mu2. So how do we get evidence? Well, we get evidence the usual way. We go and get a sample. And let's suppose I find N1, let's say it's 200 people. And I find that the mean was 112 and that the standard deviation was 8. And then we go over here and we do another group. And let's say that sample size was 300 and that the mean here was 119 and that the standard deviation was 11. Do you notice that the numbering system associates the means and so on with population 1 and the subscript 2 associates it with population 2? That's pretty standard. And then what do we do? Well, this information can then be put into SALT, and what you will end up getting when you're finished is a test statistic. Will be a t equals something, and you'll get a p-value. And the p-value is what you really want. And in these stories, you're always going to be given a significance level. In this case, I'm saying it's 0.05. So this is the whole package. I could put a story on that. The mean weight of American adults, male adults, is 112 pounds. Their standard deviation is 8. And that's what we got when we got from a sample of 200. We went and got 300 Scotsmen, and we found out that their average weight was, what, 119 pounds, and their standard deviation was 11. And is there enough evidence to show that Scots people, for instance, are heavier than Americans? You know, that might be the story that you get with it. So what I'm now going to do is I'm going to keep this information here, and I'm going to nip over, and we are going to do a SALT and calculate the test statistic and the p-value. And then we will be able to find, I hope, some evidence to prove that what I just surmised is true. So if you can bear with me for a few minutes. I'm trying to find a SALT button if I can. Right, they're hard to find actually. Right, got one. Okay, so I'll now nip over and show you how we get SALT to do all our stuff. Are you looking at SALT right now? Yeah, okay. So one sample, do you think that's the right choice for this story? Right, here's your guys you can pick from. Who are you picking?
2 sample.
Right. If it was a story to do with proportions, right, 2 population proportions, wouldn't we be using 2 sample proportion instead, right? So I think that's pretty straightforward. So 2 sample. The first one is going to be the Americans. So what did we know about them? They weighed on average 112. Their standard deviation was 8. And we got that by asking 200 of them. On the second one, the weight was 119. That the standard deviation was 11, and that the sample size was 300. Now, this number here is always, at least the questions we're going to do is always going to be 0, because that's essentially mu1 take away mu2 equals 0. So just leave that guy at 0. Now, in the story that we had, isn't there evidence that the second law is bigger than the first? Agreed? Now, that you've got to be careful on, because when you say it that way, you think that you're trying to prove greater than, right? Because Scotsmen are bigger than Americans. But if America is first and Scotland is second, and America is a little number and Scotland is a bigger number, aren't you looking to prove that the difference between them is less than 0? So less than 0 means the first guy is smaller than the second guy. Greater than 0 means the first guy is bigger than the second guy. And not equal to 0 is just that the first guy is different from the second guy, right? So that's one of the things you've got to watch. And I don't know if they're assumed equal variance. I'm looking at the samples, they're not, so I'm going to leave it alone. And I'm going to generate the results. And everything that we really need to know here is our t statistic and our p-value. And can you see in this story, the test statistic is roughly negative 8.23. And that the p-value is essentially virtually 0. It's 1, 2, 3, 4 zeros and a 1. So I'm now going to return to the whiteboard, and finish this question off. So we got our story. We are, in this particular case, weren't we looking at that one? Going in the middle. And we got this test statistic and this p-value. So all we need to do now is do the test. And the test, you kind of do this in your head most of the time, don't you? Is the p-value less than the significance level alpha? Is 0.00001 less than 0.05? And since the answer is yes, we will reject H naught. And won't we say something along the lines of, and there's significant evidence to prove that Scotsmen are heavier on average than Americans. And the story is gone. You're finished. There's not a big difference, is there, between a single and a double, really? Okay, you have to remember this mu1 take away mu2 is 0, right? That's a little different. And the three alternate hypotheses are all in terms of bigger, less than, or not 0. But most of the process kind of duplicates itself. You just do it twice instead of once. Any questions about that before we look at some of the homework questions? I'm getting some nods, so that's a good.
So Professor,
Yes?
I got the rejection part. So, but some question was asking like reject the original H, but there's sufficient and insufficient evidence. So how can I tell is sufficient evidence and insufficient?
Sufficient evidence is going to be that your p-value is less than alpha. Anytime you get a p-value that is less than whatever alpha is, that is sufficient evidence.
It's sufficient, right?
Sufficient, not
Okay.
insufficient.
Okay.
Sufficient. Okay. Let's look at some of the homework questions. It's always a good way to figure out what they're expecting of you. Okay. I got another window I want to stick somewhere. Here we go. A study represented data given in response to the question, what is the fastest you've ever driven a car? And 101 females, it's 88.3 was the average, and standard deviation is 14.3. For the males, it was 86 males, I should say, and 107, and the standard deviation is 17.3. Just superficially, would you agree that that strongly suggests that men probably drive faster than women?
Can you share your screen?
Oh, I'm not sharing my screen again. I thought I had, but I hadn't. You're right. Right. So that's what I was talking about, this stuff here. Would you agree that it looks like men drive faster than women? Not necessarily a good thing, but that's what they do on average. So we are going to use salt with a 0.05, and we're going to end up with only one answer, one of these two guys. So everything that we're going to do is inside salt, and when we pop out of it, we'll be able to say, do not reject a null or reject a null, okay? Now, won't you reject a null if the p-value is less than 0.05? That's the test. If the p-value is less than significance level of 0.05, you will reject H naught, which means I'll pick that bottom dot. And if it's bigger than that, then I'll pick the top one. The bottom one means we've proved that men do on average go faster than women. If we pick the top one, all we can really say is that there's no evidence to say that there's really any difference at all. So I'm going to have to write down all those numbers because there's a lot of them. I don't think I'll keep them in my head. So they're doing men is greater than women. Okay, that's fine. Who do you want to be population 1 and population 2 in this story? Because since they didn't tell us, we can pick. Who do you want to pick for 1?
Female.
Yeah, why not? So N1 is going to be 101. The mean X bar 1 is 88.3, and S1 is going to be 14.3. And 2 is going to be the male, so N2, there's 86 of those were asked. X bar 2 was 107.2, and the standard deviation was 17.3, right? That's all the numbers that I've got that I need. I'm going to hit this fella, and we're going to bring it over, and it's going to be a 2 sample T. And for the men, sorry, for the women who go first, because we decided it was going to be women first, this number here is 88.3. That the standard deviation for women was 14.3. And that there was 101 of them in the sample. And number 2, which is going to be the males, there's going to be 86 of these guys. Sample mean, I got the wrong number. It's me, my reading. It's 107.2. That was the average speed they went. The standard deviation was 17.3. And the number of people was 86. That's how much was in your sample. And that's always going to be 0. We are trying to prove here that I'm assuming that men went faster than women. That seem reasonable? Is that going to be greater than, less than, or not equal to 0?
Would it
Women
be less than, since
yeah. It will be. Women small, men big, right? That's a less than story. I'm going to avoid that and just generate results. And the p-value that we got was 0.07. You see that? 0.07. Now let's return to the story. Yes.
Your sample for your standard deviation for males is 117.
How did that happen? Oh, I had a 1 there. Well caught. Well, now I'll generate results and we'll probably get a better p-value. Let's find out. Maybe worse. Who knows? Oh, it is nice and tiny. Would you agree? And that means then that when we go here, oops, we go here, I've lost it. Oh, there we go. That we'll reject the null hypothesis, and we've proved that men do typically go faster than women. So far, so good. Now, I don't want to use up too much homework questions because there are so few of these ones, but disappointed that they didn't create more of them. So I'm going to give you a made up one, but I'm going to keep it really quite realistic, at least in the general sense. Let's suppose that we are looking at a new drug and we want to test it. And we want to see if it's better than the old drug, right? And we'll have this new drug. Its job is to reduce blood pressure, right? So if you take it, it'll make your blood pressure go down a bit. This is for high blood pressure patients, right? So number 1 is going to be the old drug. And we collected a sample of 200, a clinical trial of 200 patients using the old drug. And on average, it reduced their blood pressure by 5 units, and that the standard deviation was 4. And now we have a new drug. and we did a clinical trial with them, and there were 400 in this one, and the reduction was 7, and the standard deviation was 3. So can you imagine a story where the old stuff, this is what you got when you did the old stuff, and this is the new drug, this is what you get with the new drug. And the question is, have we proved to the FDA that the new drug does a better job of reducing the blood pressure? Well, if we look at it superficially, would you agree that it does reduce it more than the other one? So that's a good sign. But couldn't that just be randomness, right? You can't just say that's evidence, because we know from experience that when you do samples, they vary a lot, right? And you might get another one where it was only 4, right? In which case the new drug doesn't do as good as the old. So we have to figure this thing out. So we're going to start with our null and alternate hypothesis. And the null hypothesis is going to be mu1 taking me mu2 is 0. What will mu1 take away mu2 look like in this story for the alternate? Bigger than 0, less than 0, not equal to 0. What would you do, or you would expect to see? What would you do? Is the first thing going to be smaller than the second? Is the first thing going to be bigger than the second? What are you going to get? If you just take x1 bar and subtract x2 bar from it, it's a good clue.
So would it be less than?
It would be. So if you're not sure bigger than or less than 0, take x bar 1, subtract x bar 2, and positive numbers would mean greater than 0, and a negative number would be less than 0. Is that a nice, easy way to check it? If you're trying to, because sometimes you end up doing double negatives in your head. It's less than, but that really means the other one got bigger, and then you get confused. So we have pretty much everything that we need. So I'm going to go into SALT now. And so that means I'll have to leave this screen. Hopefully change to the other screen and you'll see it. And I'm going to use that button. And here we go. So it's going to be 2 sampled. The first mean is 5. Standard deviation is 4. And there was 200 people in that clinical trial. And in the second one, it was 7. This is 3. And there was a lot more people in that sample, 400. And I'll make sure that I actually typed in the numbers correctly, which I did. And we have already decided that this is going to be a less than world. And we're going to generate results. And bingo, then we get a really nice p-value again. And so I'm going to just return to what that might look like when we write the results in. So we would be given a test statistic. And normally they seem to like 2 decimal places for that one. So if you can trust me, it would be negative 6.25 when you round it off. And then you would get a p-value, which is more important really. And the p-value to 4 decimal places gets rounded off to essentially 0. And then you do your test. And your test is your p-value less than your significance level. If the question in WebAssign does not tell you alpha, what is my my rule for what you make it? If they don't ask you, what do you make it? Anybody remember what I just decided arbitrarily to make it?
Is it 0.05?
Yeah. So if they don't ask you, it's 0.05. If they don't mention it anywhere, you got to pick something, right? So pick that one. In this case, I think it's pretty clear that the answer is definitely yes. So won't you then pick reject H not, and that would then be sufficient evidence to prove that the new drug I'll just say did a better job than the old one. Does that make sense? So pretty much whenever you hear clinical trials being done, there is almost always, if you look back at the beginning, week 1, isn't there almost always 2 groups? There's the test group, which is these guys, right? And then sometimes called the experimental group. And then you have the status quo group, right? Where they just get the placebo or they get the old drug. And then you're comparing the two. And hypothesis testing is how we finish the job, how we can do a clinical trial, right, and get a whole load of numbers and information, and how we can take that and reduce it simply to, yep, that new drug is a better drug than the old one. Go ahead and use it, provided you've done safety checks. Not getting too many questions, but I guess that's a good sign. Are there any more? Are we getting a feel for this one? Is really just a continuation of the single mean, and it's also a lot like the 2 proportion story. It's got a little bit of that in it as well. And just remember the 2 T distribution thing, and you should be fine. Okay, let's kind of almost finish off today. I do want to finish off today, but let's see what's left to do. In question 8, I'm not going to do this one, but isn't all the numbers you need in that little table? So won't that be the sample size for N1, X bar 1, S1, N2, X bar 2, S2? I don't know if that's going to work or not, but when you hit use salt, won't you be able to do it? They told you alpha, 0.05. I don't know why they bothered to tell you that, because salt's going to do it for us anyway, so I don't really care. And we're asked to test that the mean number of hours of sleep for the 2 populations are equal, that they are not equal. So can you see this one's going to be a not equal to 0 test? You get the right answer, you get the wrong answer. And here is what the data looks like for the non-liberal arts students and the liberal arts students. Does this data look approximately normal to you? Does it look approximately normal? Well, let's see. If you I wish that writing would disappear. So I'm not going to move my mouse pointer. If you imagine my finger pointing at the screen on the left-hand side, doesn't it kind of go up and then it go down? Does it look to you that there's a skewed to the left look to it? Does it look like there's more on the left of the middle hill than there is on the right? But is it enough to be a problem? Probably not. Agreed? But it does go up and down a lot, doesn't it? And that might be a bigger problem. If you look at the liberal arts students, it goes up and down like a yo-yo as well. It's got that same a little, a big, a little, a big, a little, a big. That's a little bit worrying as well. So when they're talking about the condition for a 2-sample t-test, let me take you through the gist of what you want to be true so you can use the t-test, 2-sample t-test. First one, in no particular order, is that you want it to be a random sample. I mean, we pretty much guarantee that, don't you? I don't think I've had a story where that's not true. Second thing you want is you want the size. In other words, you want the samples to be big. Now, when you did proportions, didn't you do the NP1 bigger than 10, the N1 minus P bigger than 10, which boils down to were there at least 10 people who said yes and at least 10 people who said no. And if the answer to that was yes, you're good to go. When you're doing 2-sample worlds, you want the samples, both of them, to be bigger than or 30 or bigger, right? To be really comfortable. There's a bit of a wiggle room there. So a 27 would probably work. You know, you might not be happy, but you would do it, that kind of thing. So it's not as hard and fast a rule as the 10 rule for proportions. And the third one, you didn't need for proportions, but you do need it for 1-sample and 2-sample means. And that is the distribution of the data should be, and the keyword here is approximately bell-shaped. We also use the term should be approximately normal in shape. Yeah, whatever. You want it to look like that. Right? Now, you see that dot plot that we had? Didn't it look more like this? Do you see that that's not really that shape? So that's why I would be a little bit wary on using that data to come up with any conclusions. Now, approximately does mean that you can be a little bit skewed to the right and we can live with it. Because in real life, real data, you very rarely ever get perfect single hills, very symmetric, very balanced. Isn't there always going to be a little bit out here, a little bit out there? You got to expect that, but that's okay. What you can't have is data that is very skewed to the right. Would you agree there's probably going to be some grey area between this is okay and that's not okay? Yeah, like how far more can you go before it stops being okay? And that is really a judgment call. I wish there, I mean, there are ways to do it. One of the tests that you can use is find out if your data has any outliers. You know how you do outliers, just find the z-scores for the big ones. And if their z-score is bigger than 3, you got problems, right? And so you might be, it might be a good idea not to do the data, right? And if you look back at my video on single proportions, it's essentially the same story is true. All we're doing now is that both populations have to follow the same rule, right? It's no good if one of them is lovely and bell-shaped and the other one is like all over the place with no shape at all. Right? If one population is good and one's bad, you're still not going to be able to do the analysis. That makes sense? You're comfortable with that? So now that we've kind of talked about that, we're almost done. Time for judgment call. Do you want to use this? Do you want to use it now? Now that you've seen what the data looks like. Okay, well, since there's 3 of you, I can ask each of you. Olivia, do you want to use it?
Sure.
Okay. Sal, do you want to use it?
Yeah.
Jana, do you want to use it?
Yep.
Okay. I don't want to use it, but that doesn't mean I'm right. It could be that you lot are right. Because when it's a judgment call, it's kind of hard to say you're wrong because that was your judgment, isn't it? I wish it was more strict than that, but thankfully they don't give you many questions where you have to do it. So what I'm going to do is let you have fun doing that. And if the first time round your judgment call works, then you say, yep. And if it doesn't, well, you pick my judgment call because there's only 2 directions, right? You either do or you don't, right? Moving on to this one. I don't know if I need to do that. Are we comfortable that that's just another one of the same stories that we've just been doing? Okay. And that is us. We are finished. Thumbs up, good. So what's going to happen is that you only have to get up to 12 ABC. And then next week, by Wednesday, you have to do 13A and 13B. I would just bite the bullet and just do the whole bloody lot, because doesn't that mean next week you can just get ready for your final? Just study up, get, everyone's out the road, I'm done. That would be my advice to you, not just you, but anybody who's listening to this. That's as far as that's concerned. I'm now going to hang about for officers. So if any of you have homework questions or just whatever, you can hang about. I'm going to do another one of these tomorrow, but it's really just going to be a normal officer one tomorrow because we have kind of covered the work. Well, actually a little bit quicker than I thought, but that's cool. So you can drop in and it'll be the usual 12 o'clock. So we're back to 12 o'clocks now. And next week, 12 o'clock officers, I'll probably do more officers in the last week because 12 o'clock might not fit everyone's schedule. Okay, if that's it.